How do you teach a machine to learn from something like a social network or a molecule? I mean, think about it. Unlike an image, which is a nice, tidy grid, or text that flows in a sequence, graphs are, well, they're kind of messy. Their entire value comes from their connections, not their physical layout. So how do we build systems that can actually understand these complex, interconnected webs? Well, the answer takes us on this fascinating journey that connects computer science, geometry, and even physics. Let's dive in. We're going to look at this problem through 3 different lenses, and you'll see how they all connect. We're going to start small, at the micro level, where nodes are just talking to their immediate neighbors. Then we'll zoom way out to see how all those little local chats actually reveal the graph's global structure, its fundamental shape, if you will. And finally, we're going to connect it all to the physics of how information flows over time in a process called diffusion. It's a story that ties together algorithms, geometry, and physics in a really beautiful way.
All right, so first things first. Why are graphs such a headache for machine learning in the first place? The whole challenge really boils down to their irregular structure.
Just take a look at this comparison. An image is perfect. It's a predictable grid. Every single pixel has a clear up, down, left, and right. But a graph? A node just has, well, neighbors. There's no natural ordering, no first neighbor or last neighbor. We can't use its position for anything. We can only rely on its connectivity. And that means we need a totally different kind of algorithm, one that just doesn't care about order or where things are located.
And this brings us to the golden rule for any algorithm that wants to learn on graphs. It has to be permutation invariant. So what does that actually mean? It just means that if I shuffle the order of a node's neighbors, the algorithm's output better not change. The final result has to depend on the set of neighbors, not the specific sequence you list them in. This one single rule basically shapes the entire field of graph neural networks.
So how in the world do you build an algorithm that respects that rule? Well, the most intuitive answer comes from our very first perspective, the network view. And it's all built on an idea called message passing.
The idea here is actually super simple and really powerful. At every step of the process, each node in the graph does 2 things. First, it exchanges information with its neighbors. You can think of it like each node broadcasting a question. Hey, what do you all know? Then, it takes all those answers, combines them with what it already knows, and updates itself. It asks, okay, based on everything my neighbors just told me, how does this change my own perspective?
Now, when we formalize this, it gets really interesting. A single layer in what's called a graph neural network, or a GNN, breaks down into 3 steps. First, you compute a message from each neighbor. Second, you aggregate all those incoming messages. And here is the absolute key. This aggregation function has to be permutation invariant. Something like a sum or a mean or taking the max. Why? Because it doesn't matter what order you add up a bunch of numbers in, the sum is always the same. Finally, you take that one combined message and use it to update the node's own state.
Let's make this totally concrete. Take a look at node 2. Its neighbors are node 1 and node 3. In this really simple setup, the message is just the neighbor's value, and the aggregation is a simple sum. So to get the new, updated value for node 2, we just take its current value, x2, and we add the values from its neighbors, x1 and x3. It's like node 2 is just soaking up information from its immediate surroundings.
Okay, but doing this one by one for every node would take forever on a big graph. So we use the magic of linear algebra to do it for the whole graph all at once. Now this equation might look a little scary, but let's break it down. The A here is the graph's adjacency matrix. That's just the map of all the connections, and it's what handles passing info between neighbors. But notice the plus I, the identity matrix. Why is that there? It's absolutely crucial. Without it, a node would only listen to its neighbors and completely forget what it knew a moment ago. Adding the identity matrix creates these little self-loops, making sure each node talks to itself and carries its own information forward.
Okay, so message passing is a really powerful tool. But is there a deeper principle at work here? Let's switch to our second lens, the signal view, and start thinking of the graph not just as a network, but as a structure that signals can vibrate on.
The main goal here is to turn the graph into vectors. Machine learning models love vectors in a geometric space, but a graph is just a bunch of abstract connections. Spectral embedding is what builds the bridge. By using the eigenvectors of a special matrix called the graph Laplacian, we can actually assign geometric coordinates to every single node. It's a way of translating the graph's web of connectivity into a language that normal machine learning algorithms can finally understand.
And this is where the idea of graph frequencies really shines. Just think of it like sound. Low eigenvalues correspond to smooth, low-frequency signals that change very slowly across the graph. kind of like the deep bass notes that give a song its underlying structure. High eigenvalues, they correspond to noisy, high-frequency signals that jump all over the place between neighbors, like high-pitched static or feedback. And just like with music, we often care a lot more about the structure, the bass, than we do about the random noise.
So we've got an algorithmic view with message passing and a geometric view with these spectral frequencies. Our third lens, the physics view, is what's going to unify them both through the dynamic process of diffusion.
And here's the big punchline. A simple graph neural network layer is mathematically the exact same thing as one step of a diffusion process. Every single layer of the GNN is literally spreading a signal out across the graph, just like a drop of ink spreading out in a glass of water.
Now, we need to make a really important distinction here. This is signal diffusion, which is all about local averaging. Think of it like this. With signal diffusion, if all your neighbors are at a temperature of 50 degrees, your temperature is going to become 50 degrees too. This is completely different from something like probability mass flow, where if your neighbors give you 10 units of stuff, you now have 10 more, and they have 10 less. GNNs work by smoothing through averaging, not by moving mass around.
And here is probably the most profound connection of all. This discrete diffusion process happening on the graph is a direct analog to one of the most fundamental laws of physics, the heat equation. What we are doing inside a simple GNN is modeling the exact same fundamental dynamics that describe how heat spreads through a material. It's a powerful, direct link between modern deep learning and classical physics.
Okay, now let's bring it all together. By combining these three views, the network, the signal, and the physics, we can finally understand a fundamental limitation and a core design challenge in all of graph learning.
Because GNNs are just performing diffusion, they act as a spectral low-pass filter. Just look at this graph. For the low frequencies, the small eigenvalues, the filter factor is close to 1. That means the signal gets preserved, it passes right through. But as the frequency gets higher and higher, the filter factor just plummets down to 0. Diffusion effectively kills the high-frequency treble, all the local details, while preserving the low-frequency base, the global structure.
And this slide right here synthesizes our entire journey. Local message passing is just discrete diffusion. That diffusion process acts as a spectral low-pass filter. And if you let this process run for too long, if you stack too many GNN layers, you get a problem called oversmoothing. The filter ends up eliminating all the frequencies except the very lowest one, and every single node in the graph ends up with the exact same value. They become completely indistinguishable from one another.
So what have we figured out? Well, we now understand why GNNs use message passing in the first place. It's the most natural way to deal with permutation invariance. We can see this whole process in a new light as a filter that prefers global structure over local detail. We've connected it directly to the fundamental physics of diffusion. And most importantly, we now know the inherent danger of this process. If you make your GNN too deep, you run into oversmoothing and you wash away the very information you were trying to learn.
And this leaves us with the central design tension in all of modern graph learning. It's a balancing act. You need deep models with lots of layers so that information has enough time to travel across the entire graph, letting nodes get a global perspective. But every single layer you add increases that smoothing effect, destroying the local features you need for your predictions. So the real question becomes, how do you build a model that can see the whole forest without making all the individual trees look exactly the same?